Hello, this is section 2.12 on the resonance hybrid. So a resonance hybrid is the kind of final point of the discussion on resonance forms that we talk about, because finally bond line structures have some way to talk about how resonance structures actually impact the molecular structure that we draw in the bond line structure itself. That's a lot of words and doesn't seem like they make a whole lot of sense, but hopefully here in a second it makes a lot more sense. So if you remember, we talked about how in some molecules, like this carboxylic acid, for instance, or carboxyl anion, let's say, gives us an idea of what the functional group is, but doesn't necessarily tell us about how the molecule actually acts, because it can't account for resonance. And resonance here happens very easily. It's a bad. There we go. There we go. Happens very easily to give this structure, where each oxygen technically could have the minus charge, or each oxygen technically could be neutral charged. So because each of them have more or less equal probability for them to have the negative charge or the neutral charge, um, we have to come up with some way to meld these ideas together, because these are the two resonance forms, and so the chemistry of this functional group should reflect these resonance forms. So in bond line structures, we can draw the resonance hybrid, which is essentially just an amalgamation of these two. I'll draw the reverse arrows for this one first. There we are. And the hybrid, the resonance hybrid for this would look something like this. Whoops. Silly. Okay. I better, oh. There we are. Draw in little brackets here, the resonance hybrid. Hybrid. Great. So here you can see we have done two things to indicate this is some kind of hybrid structure. First, we've put these little dotted lines in here to show that it's kind of like a double bond, it's kind of like a single bond, it's in between. We've done that for both bonds because both of those bonds are the ones that change with resonance. Last, we put partial negatives on both oxygens because either of them could have a negative charge or a neutral charge. So this means that um, their sort of observed charge would be somewhere in the middle, not totally negative and not totally neutral, but partially negative. And with these resonance hybrids, you can do um, you can use this for a large amount of functional groups. Like for instance, one more we can do is a classic example. Here we have some amide, and a really good resonance form for an amide has this structure. There we are. It has this structure, and of course it can always go back just as easily. And even though in the last section we learned that having two charges isn't necessarily good, the minus charge is on the almost electronegative element, and the positive charge is on the most electropositive element, which means that this resonance form is probably pretty stable, even so. And not only that, but we can draw a resonance hybrid for this molecule that looks something like this. You don't actually draw the lone pairs in a resonance hybrid. Sorry about that. You draw the partial positive here on the nitrogen and the partial negative on the oxygen. There we are. So now you can see that in the amide structure, the nitrogen is partially positive, so that lone pair doesn't really act like a true lone pair. And in oxygen, it's partially negative, meaning that it is going to act as if it has more of a negative charge, more electron density on that atom. Okay, and this has been section 2.12.